Hello, welcome to this talk. I'm Luis Lopez. I'm a software engineer at the National Snow and Ice Data Center. Thanks for PyData for organizing this event under these circumstances. And thanks to NSIDC for allocating some resources for this talk. We're going to talk a little bit about what the basic of climate change and some of the remote sensing data that is useful for scientists so they can get a better understanding of this phenomena that it's so important for everybody to know and understand. A little bit about the data center. We are based in Boulder, Colorado, and we're part of the University of Colorado Boulder, and also we're part of a bigger organization called Cirrus, which also gets funding from different sources, but the main source of funding for us is the National Science Foundation and NASA, and we're one of the 12 data centers that stores and distributes the NASA Air Observing System data sets. So all the satellites that NASA has and are processed and that distributed are separated kind of by the type of missions. And we distribute data that are related to the cryosphere. So that's what we do. We also do field research. Our scientists go to the frozen regions of the world to install some instruments. They also publish papers and they do science in general. And so we're going to talk about why climate change is important, what climate change is very briefly. You probably have seen this graph before. This is the atmospheric carbon dioxide, and this is almost 1 million years. And there are a lot of, people that doesn't believe in science, that don't believe in science, that are like claiming, oh, but the planet was warm before. And well, this is one of the best ways that we have for measuring that. And this is from ice cores, the analysis of this many years. And it wasn't that hot. The variation has been between 180 and 250 to 80 for almost 1 million years, and now it's through the roof. And the main driver of that, Jeff Sachs is an economist from Harvard, now working at Columbia. Their institute says it's all about scale. We've really been successful as a species in the last couple of hundred years since this industrial revolution, and we modified the planet. There is this term called the Anthropocene that a lot of scientists think we're living in that. We're modifying the environment to that point that, if there is an anthropologist or archaeologist in 1 million years from now, they'll find evidence of our existence and in how the planet behaved these years. And one of the consequences of this is that we have more natural disasters every year. So the things that happen 1 in 1,000 years are happening way more often. One of the examples this year has been the wildfires in Colorado and California. And this is fine, but not really. No, it's not fine. So climate change is a complex problem. It's not, just measure the temperature in the ocean and that's it. There are a lot of systems at play in the planet, and even for simple system interaction between simple systems are complex, like this Lorentz attractor shows. So now scaling that, it's way more complex. But the good thing is that scientists are figuring out these processes with the help of data and algorithms recently. So what they need in order to do this is have good historic records and good algorithms. So I'm going a little bit fast in this part because you, as I said, probably are aware of most of these concepts. And I want to dive into the actual Python analysis in the Jupyter notebooks. This is talking about the open science revolution, like why that is important in the analysis of scientific data. And the main thing is that you can have access to research and the data that was used to do that research, and that you can replicate the results to advance your science. In this case, for climate change, we're going to talk about remote sensing. So this is timeline for what remote sensing is, and it's really very recent that we started to do this kind of measurements. If you go, 1,000 years ago, the only thing that were recorded and that was important for the agriculture was probably precipitation and temperature, and that gives you an idea of very and I'm talking about active recording, because of course we have indirect ways of measuring how the planet behave in years that are like in millions of years, and as the ice core records show in the first slide. So, but remote sensing, it's a recent thing. So what is remote sensing? It's a process of monitoring physical characteristic of the planet. And these physical characteristics can be taken from satellites or airplane, but basically they're like passive or remote sensing instruments that will result in a data set that gives you multiple characteristics like temperature, chemical composition, topography, and other derived measurements. So these are some of the satellites that are being used. Some of these are decommissioned, some of the new ones are not there. And this is just from NASA. Of course, Japan, the European Union, they have their own constellation of satellites working, taking different kind of measurements. So what happens once that the satellite, this is when the interesting part starts for data analysis. Once that they take this data, the instrument send it to Earth, then they are encoded in a data structure, and that can be, raster, vector, point cloud, n-dimensional arrays. You see two examples on the right. On the top is a raster. On the bottom is, it's a raster, but it represents LiDAR data from another mission. And the common thing between all the remote sensing is that you're talking about physical measurements with a geolocation and resolution. So that's what remote sensing data is. And these are different levels of data processing. Like when the satellite takes the instrument, takes the measurement and it's very raw, then it's like the analogy could be in a camera when you take a photo in raw mode and you have correlation almost 1-to-1 between the zeros and one and what the sensor did. And then the image that has compression, that has other processing things. And finally, if we keep extending the analogy, then you can apply filters to the image. So that would be the same for remote sensing. And science usually starts in level 1B, not in level 0. So once that the data is projected or gridded into a projection, we need to be aware of these other things that will cause some caveats when you are analyzing it, which is the distortion that produces. So you have to work in the right projection for the data. And in our case, that we're working a lot with polar data, this projection, the classical Mercator, is not very useful. So we need to work with polar projections. So we're going to analyze a little bit of the Python landscape with remote sensing data and geosciences. So you probably heard about some of these packages. We use some of them at the center to generate some of the data that we or process these higher level products that we distribute, and not all of them. We want to adopt a more cloud approach in recent months, and it's on the route for what's coming in the center in the next year. And also, I'm going to talk about that at the end. So here are some examples of if you look for the data in our website, you'll find a lot of information and different data sets of remote sensing data sets, most of them. And so all of this data is distributed in a format, right? So we have data that can be plain text and CSV and GeoJSON shapefile, depending on the nature of the data. But the cool thing about Python and this ecosystem that it supports a lot of this format. So there is a one-to-one, almost one-to-one relation between what format you're working on and what Python provides to you for analyzing, just for reading the data and start working with it. This is a data set that is kind of famous. Well, it's one of the most prominent data sets that we distribute as the CI610. And at the moment, we distribute it in binary, but the thought is that we'll have to process it and distribute it in NetCDF. The facts are on the left. You can see the graph that it produces if you zoom all the area of coverage for CIs. And this is important because it reflects the status of CIs in the pool, which is kind of like one of the main measurements of how the planet is doing in terms of warming. Ice reflects light and cools the planet, and when you don't have that radiation is absorbed by the open water, the open ocean, and well, it's a negative feedback. So this is a different data set. This is LiDAR. We're going to analyze this in a Jupyter notebook in a second, and the thought is that we're going to try to harness the power of Python for making the life of scientists easier when doing this kind of analysis. And the secret ingredients are Dask, which is a framework that allows us to scale horizontally. If you hit one of the two cases where you don't have enough CPU power or you don't have enough memory to fit the data sets into your computer, so then you can use Dask that wraps the other libraries like pandas and NumPy, so you can distribute this work among different clusters, different nodes in a cluster, and you can see at the bottom how that work is being scaled and doing at the same time in multiple cores. And the other secret ingredient is Jupyter Notebooks and its widget that we are just starting to use, or we will have like a couple years of using them, and it's been amazing to have this ecosystem of libraries that you can use in an interactive environment like Jupyter Lab, Jupyter Notebooks, even in a Jupyter Hub for multiple users to do data science. And we can all agree that that's probably the de facto for data science, no matter if it's geospatial data science or different topic. And one of the things that we wanted to do or are doing at the center is like trying to make this workflow simpler for a scientist. Like they usually go and start with a coffee their day. They download the data from a website. If the data is not that big, they load it into a Jupyter notebook. But we can start from the Jupyter notebook. So we're going to see how that it's going. So a couple projects at NSIDC for analyzing this remote sensing data that are directly related with climate change is like how fast glaciers are melting. So yeah, it's not as simple as just going to Greenland and you can start doing local measurements, but there are more efficient ways of doing it, doing these things. So are these scientists right? There is a senator from Texas that says that global scientific evidence doesn't support global warming, and we'll see if that's true. So we're going to use Landsat imagery for doing this quick analysis. Landsat, it's a mission from USGS and NASA that takes scenes from the air. Basically, they take a photo of the same place and are in repeated occasions, and they overlap. So you have a very good stack of how that particular region is changing. So it's used for different purposes like water management, forecasting, and all that. But in this case, it's used for deriving the velocities of glaciers. So if you see in these two time lapses, you can see the different features in the surface moving. So you can get an idea of how fast they're moving, not an idea, a precise calculation of that. The PI, the principal investigator for the project, is Alex Gardner at JPL. And we've been working in this project with him for like a year now. And the data set for this project was just released a week ago. And you can ask me or email me about that information. But this is the final product in the website form because, well, you have to do a website. you see the velocities, the map velocities, the mosaic of Greenland here in a map. You can like go to the website and explore it and select a region and download the data like we were talking about. But you can also do this in a Jupyter notebook. So you can get an idea of how that's working. And I'm gonna share my Jupyter lab with you. So this is a new approach that we've been taking at the center for this kind of data. As I said, instead of taking the scientists to a website where they download the data, we want to use a Jupyter notebook so they can like do everything here. And in order to do that, we've been using this amazing widget that it's called IPyLeaflet, which lets you render a map in the notebook. And you can do kind of like almost the same things that you could do in a web portal, but here. So some data visualization, in this case, exploration of the data. This is an example of how we are going to, or a scientist can like just drop this circle in the map and they can like say, well, for this circle, I want to get all the velocities here. And you can select the range and you can select the amount of valid pixels in each of those, because you have clouds and different artifacts when you're doing this analysis. So, for example, in this, I just want images that are like 80% valid or greater, and from starting in 91 and ending, let's say, in 2009. So with that, you can start doing the, hey, can I see like how many granules are each year, and you get this timeline. It's really fast. The backend for this is PostGIS, and on top we build, and that's the general approach at the center to build this. The word, has now a different meaning, but microservices on top of geospatial databases, like mainly PostGIS, for the metadata, right? So then you have the counts for each year, and then you see that the files for this data set are hosted, despite that we are collaborating with NASA, they're hosting it at the JPL domain in AWS. So down the road, that allows us, or will allow the scientists to do cloud based analysis, and they won't have to download this data. Because it's big. So I'm gonna just filter some. What I'm doing here is I'm saying for this example, I just want this many files. I don't really want a lot of data, because what we're doing is trying to teach them how to work with the data. So you can see the data is per granule is not that big, and it almost instantly downloaded it. So then you can start working with the data, saying, okay, so this is where the center of the selection is. These are the velocities. It's really fast. And then you can like even graph the data, saying, well, in 2001, the speed of that particular region was high, and now it's has the crest. And you can even plot the one of the scenes from Landsat from that region, say, oh, well, you see the change in the speed, right? So that's really cool, I think. And this is the first iteration that we have been working on. There is another project that I wanted to talk to you, and I'm gonna share a different, going back to the slides. So here, well, this data set, what it's giving us is the speed of the glaciers, right? In a global scale. But that's not everything. You also need information about mass, and that brings us to another project and another data set that does basically that with LiDAR data, and that's called the Ice Flow Project. This project it's cool because on top of just doing that, the source for generating this, well, it's not just one satellite or one mission, but we had to come up with a way of consolidating data sources from different institutions and missions. So space lasers. Oh snap! There are so many, and if you want a time series, you'll have to deal with all of them. And one of the issues that we had with this project is that the Operation Icebridge, which is the main data that we're covering here, comes from NASA, but also comes from different universities. And for sure, they thought that they didn't thought we're doing something particularly wrong, but each of these universities or research institution had a particular way of, or the instrument even had a way of recording things. So they're in even different formats. And so if you're a data scientist, climate scientist, it'll be very difficult for you to read all the documentation and start from the binary data and to try to build that. So what we did with this project was to consolidate that. We ingested all the data from all these missions, except ISA2, which is really huge, and it's a new one. We're going to work with ISA2 as well. But the previous missions, we consolidate that. So once that you order the data, it'll be standardized in HDF5 format, which is one of the scientific formats for working with remote sensing data. And so we're going to go back to the notebooks. See here, same approach. We're doing what would be a data tutorial. All of this is open source on the NSIDC GitHub organization. We're giving an explanation of what we're doing, the coverage of the particular data sets from each of those missions that we're going to serve. These Earth data credentials are so we can interface with the NASA Common Metadata Repository, which is where NASA indexes all the metadata about the Earth observing systems. And you don't need to be a NASA employee to create an account, but NASA requires that so it can keep track of the usage of the data and the users. So I'm not going to log in into NASA because I already downloaded the data. Notebooks, IceFlow. So you can see I downloaded 2 granules. This is 2.7 gigabytes. This one, it's way smaller. So it's not a trivial data granule. And again, we're going to work a little bit with some of the widgets that we created for, let me restart the kernel and all the outputs. We're going to work with these amazing widgets. Sorry. So you can see here the flight paths of the mission, because the main instrument for this data was the LiDAR that was on board of these flights that NASA flew during several years, mainly in Greenland and Antarctica. So the scientists have an idea of where the density of the data, the breadth of the data lives, and they can do their selection. So they can like draw a polygon here, a bounding box, and you see where there is more density of flights is where you have glaciers that are speeding faster, because that's what the scientists are interested on, and knowing the physical processes that make these glaciers go fast. And you can also disable some of the layers, so you get a better idea of what you're trying to do here. And you can select different data sets. You can change the projection, go to Antarctica. You see the flights. We're still generating the velocity tiles for Antarctica. So you see here, and you can start doing your order. Or the other thing is that you don't really need to use this. If you are a Python user that knows how to talk to APIs, you can Well, talk to the API. And we have this, gonna close this widget for a second. And you have this Swagger documentation of the different data sets and how you can access, like if you want this kind of data, the parameters that you need to do. So you can basically build a client for this interface. And you post the order, you say, I want this kind of data set. And then you will have the order ready. And it takes, depending on the size of the order, it can take like some minutes up to hours, depending on if you're asking for gigabytes and gigabytes or just like a small glacier and some megabytes. Then you download the data. And what we're doing on top of, doing this ordering here in the notebook, we're also trying to teach the scientists how to work with that data once that they have it in their laptops, in their machines, kind of pushing where it's possible with a single node, because you don't always have AWS credits, right? So then you can use these libraries that are well known in the geospatial community for analyzing the remote sensing data, X-array. It's amazing. It's an extension of NumPy with annotated axes for multidimensional arrays. And it does some of the things that you probably might want to do. Like if everything is in the same projection and you stack those data frames, it will align them. And it provides also an API for doing some analysis. And Bags is another fantastic library that I'll show here. So gonna restart and we'll live code for a couple seconds. Well, run the cells. Okay. So here I'm saying, well, I want this file. I want to analyze this file and import these libraries. And I'm doing that so when I'm timing the running time of these cells, the importing doesn't get in the way. And the reason is I wanted to show you like why these libraries do kind of the same thing, but they're like a little bit different. And you need to know how to work with different data sets. So for example, what I'm doing here is like we wrote a client for this API that will give you a data frame. So you go from very raw data from the satellite that I mentioned, level 0, to post-process HDFI that you can load into a Jupyter notebook, and you get the data frame. So isn't that amazing? I think it's really cool for the scientists to start like doing all the data messaging and start with a data frame, right? One of the things that we're doing is like doing it. We're planning to do a Dask implementation of this in a local cluster, local machine. And in the meantime, we're using Bags for big data. So it's an out-of-core library. It allows us to do these kind of things, but faster than Pandas. And you see the time for these calculations were 49 seconds. Bags was 12 seconds. And well, what this photon data looks like in the big picture, and this is you see these are different flight lines for the mission. So the plane flew on each of these lines, firing the altimeter, the LiDAR instrument. And what we're seeing here is from the top. So we're seeing the flight lines from as if we were in a satellite. So this is Jakob 7 again, because we have a lot of flight lines in that crisscross. And once that you have multiple lines in the same place, you can do science calculating the difference, the elevation maps, and do a differential on the different dates. So you can see that with, for example, it's like you have the velocity, with this the change in volume. So then you can start, or the scientists can do analysis like mass balance. And that concludes, well, they use mass balance for doing forecasting of sea level rise, for example. if I go really into the map here, okay, so I'm zooming in at one of these crosspaths, and you see the photo, the individual photo being recalculated dynamically, and that's really cool. And this data, if you want to plot it, or the scientists want to see where exactly it is, well, then you have to use other libraries like Cartopy that allows you to put a map in the data. And well, the boundary here is Greenland. We can zoom in, but to give you an idea, or give scientists an idea of in this scale where the data is, you have this Cartopy library that it's also projected. It's not using the regular projection, so you have to adjust for that. It's North Polar stereo. And this is one of the other visualizations that we do about LiDAR data. So one of the cool things about the Jupyter notebooks is that you can have these amazing interactive widgets. And we decimated the data so we don't clog the user interface, but you see the topology of the terrain. And you can even fly with the, like if you were flying with the sensor and seeing the change in topology in real time. And I think this is priceless for the scientists. So when they go to a particular location, when they want to do an analysis, they can do it in 3D. You see the pattern of the instrument, those circular swats from the top, and then you can rotate it here, and you have this 3D tool here without using well, one of the external tools for visualizing 3D points. And so the next thing will be like based on this, you can, like I said, do calculation like different, well, the volume change in a particular place for the crosspaths. That's one of the main things. And of course, this is an incomplete thing because, as I said, we need to integrate this with the system that it's the most recent, which is ISA2. We probably want to have something like Dask implemented at the center, so we can do all this amazing stuff in a cloudy way. And there is this other project called Pangeo that it's, I think, pushing the boundaries of geospatial analysis. Going back to the slides just to finish. So not a lot of time here. I already am over the hour. Okay, so these were some of the projects and what is all in terms of remote sensing analysis, what we are doing now, and what we want to do in the future, or what will happen in the future. All this work wouldn't be possible if people, really smart people that work with me, and they're way smarter than me, were thinking that we can do better. And we never say, oh, we always done this way. We're always trying to make things different. And well, the reason is that this is a very, very important issue. We really need to understand the dynamics of climate change so we have a better forecast and we can prepare. So I think I was talking about Pangeo, and they're doing just that. They're pushing the boundaries of geospatial analysis. And it'll be really amazing once that most of these data centers adopt this approach of, to the extent possible, that we should build a system on top of the data, and the scientists don't have to download the data or even query the data, but do these calculations in the cloud. So, and of course, being able to reproduce it. One of the other things that I wanted to show you is like we always get this request for doing things that make sense, like standardizing the data, and we're working towards that to have analysis-ready data for all the scientists, or close to that. And Python is helping us a lot at the data center And with that, I would say thank you. Thank you for listening to this talk. If you have any questions, that's my email, and that's my handle for GitHub and Twitter. So it was a pleasure. Thanks to PyData for organizing this. Bye.